I'm going to explain you the meaning of covariant and contravariant vectors because they are very commonly used in general relativity. And if you want to really learn general relativity, and if you don't have intuition and meaning of these vectors, then you won't be able to get through in that subject. Let's start with the basic things first. What's a vector? Well, vector is something which has a direction and a magnitude, right? So let me show you this pen. Now this pen has a magnitude, which means that it can be a small pen or a bigger pen, and then I can move in various directions. That's the direction. So a vector has a magnitude and direction. And we can, choose a coordinate system that tells us what direction and what magnitude that vector would have. Like this is the simplest case in which we are using a Cartesian system where the coordinates x and y are at 90 degrees to each other. It could be, east or west or north or south, could be anything. This is the simplest coordinate system, and the vector or the pen's projection onto these axes form the magnitude and the direction. So we can say that the pen is, it's not the pen, it could be anything. The magnitude is 10 meters and it's in the x direction. Now a hat basically tells that this is the basis vector, which means that we are measuring it along the x direction, and in that case the basis vector is meter, which means 1 meter. It is made up of meter sticks. Sometimes you can also use I as x in place of x direction. This is just some notation. You can use x, y, or z, or you can use I, j, or k. They mean the same thing. Bottom line is a vector has a magnitude and a direction. Now in general relativity, we use indices to represent the same thing. So a same vector, like a pen, can be represented, the magnitude you can write like this, where this is an upper index, and this is the basis vector, like the x direction, and then you could put a lower vector. So you can see upper and lower. There is a symmetry here. You would say, why not put this also upper here? It's a convention, and it's a good convention, as you will see. It makes sense when you do more complicated calculations. So you can see that this is an upper index, and it is also called a contravariant vector. Now, if you want to think intuitively, what does a contravariant vector means? You think of as meter sticks. If you want to measure anything with a stick or like a ruler or something, that would represent a contravariant vector. Now, why do we call it contravariant? Well, you'll see here. This is the basis vector, which means meters. This is also the basis vector, which is centimeters. These are the magnitudes. Now, if you change the basis vector, like here, from centimeters to meters, we have made the basis vector bigger. If you do that, the magnitude goes in the opposite direction. So increasing the basis vector leads to decrease in the magnitude of the upper index vector. That's why it's called contravariant vector. It contravaries with the change of basis. That's what the name means. On the other hand, there is something called covariant vector. That does the opposite. So it has a very symmetrical structure, which means it has a lower index on the magnitude and upper index on the basis vector. So they are called lower index vectors. And an example of this would be a gradient. You know what's a gradient? Gradient means like going uphill or downhill, or measuring the thickness of an object. So let's see here. If this is a rock or something, or any body, and it has a different density of different places, and if you have to represent gradient with the use of this covariant vector. So if this is a thick place, you will draw more lines here. If it's a thin place, you will draw less lines here. So more lines represent bigger basis vector. And if there are more lines, which means bigger basis vector, the magnitude is also higher, which means it represents higher ground or higher thickness. So you see the covariant vector co-varies with the basis vector. You make basis vector bigger, the magnitude also increases, as you can see here. In a thin area where the magnitude is less, the basis vector is also less. This is as opposed to the contravariant vector. That's what these names means. Now, the other important thing to note is that the covariant vectors, they represent the parallel projections on the axis. You see, we have seen that the contravariant vector, it's perpendicular projections on this, but the covariant, like you see here, the basis vectors are not at 90 degrees. They are kind of inclined. So if you draw parallel lines, like this thing is parallel to this thing is parallel to this, so these projections are covariant, these projections are contravariant. Now in this case, covariant and contravariant means the same thing. These are perpendicular to each other. But here, if you draw the perpendicular thing, this is the perpendicular. Clearly this and this is different. So in this case, covariant and contravariant vectors are not the same. And this you will see a lot in general relativity. Let's see. Now, when you see a equation like this means summation, which means the magnitude and the directions, they are in different directions. So, this could be x direction, y direction, z direction. So to represent a vector, you got to sum up all the directions. And usually you have to write a summation sign here in mathematics. But Einstein said, I don't want to keep writing these. It's implied when there is upper and lower index. That's what it means. The other thing you will see is contraction of indices. You will see these indices being, get rid of. And, that's a very important operation. So here you will see an upper index vector and a lower index vector. They combine to form a scalar. What do you mean by a scalar? Scalar is something that doesn't have any, doesn't depend on any coordinates. This you can think like a square plus b square, right? This is like a square, this is b square. Here, because, if you are thinking in terms of the Cartesian coordinates, there's no difference between contra and covariant vectors. So there's no point of these indices. So that's why you just write v square or a square. And it tells you the length. It's just like saying that this is a pen. You can't change the pen. You can change its direction. You can change the coordinate that you want to measure it in. But the pen won't change. That's what this represents, the pen. The pen is a scalar. You can measure it in centimeters. You can measure it in meters. You can measure it in, kilometers, whatever. The pen does not change. Your coordinates may change. So hopefully you have some intuitive idea about the contravariant and covariant vectors and what do these indices means and what do you mean by contraction of these indices, what an upper and lower index vector means. That goes a long way in learning general relativity. If you want to know more about the subject, I have written a book on general and special relativity for beginners, and the link is in the description of the video and it's available on Amazon. Thank you for listening.